the idea was to give a curtain raiser. That's why I've called it a curtain raiser, because obviously I can't tell you everything about quantum computing, but the idea is to tell you a little bit about quantum computing, and it's to tell you enough to get you hooked, to get you interested, and maybe think about this as one of the areas that you want to pursue now that you're completing this program, right? So I guess everyone here has heard of quantum computing. Yes. Yeah, if it was a smaller class, I would have said, what have you heard about quantum computing? But anyway, we can maybe do that later. So feel free to interrupt me at any time. So are there also people logging in online, or is just this, right? Okay, fine. Okay, so of course you've heard of quantum computing in the news. So, but I just thought I'll start with a little bit of a dampener, so to speak. This is a quote from Serge Haroche, who is a physics Nobel laureate. He won the Nobel Prize in Physics in 2012, essentially for this, right, for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So in a sense, it was his experimental work which pioneered at least one of the current architectures that is being talked about for building quantum computers today. This was something he said in an interview when he came to India in 2012. So I think this is a tricky bit, at least for those of us who are working in quantum computing, who have been working on quantum computing for a while. Today, there seems to be a staggering amount of news about quantum computing. It seems to be everywhere. If you read any scientific page of any journal, any newspaper, anything, you are sure to find in tech news, in science news, some mention of quantum computing at least once a week, maybe, if not more often. So, yeah, so there is this issue, and I wanted to lay it out there right at the beginning. So even this Nobel laureate is saying that today we are trapped between hype and hope, okay? And he said this in 2012. 11 years later, if anything, I would say there's more hype, but there's also more hope, okay? So we are very much still trapped between hype and hope, except that our baselines have shifted. The hype is somewhere, but the promise and the hope also correspondingly has shifted. So if I'm not a soothsayer, and several people sometimes ask me, my students, and when I teach a course on quantum computing, people want to know, when are we going to see this actually a reality? Is this reality? And so on. I must tell you that I learned the subject in 2005, okay, 18 years ago. And I asked my instructor, or there were people in my class who asked my instructor the very same question. And at that point, he had said maybe in 10 years. Turns out he wasn't too far off the mark, because sometime around 2016, we started seeing the idea of quantum processors being put up on the cloud. We heard about companies like IBM actually starting to put out devices with a few qubits on the cloud that people could actually go access and so on. So that brings me to the next news item, which is 2019, which is when I think the hype really started to take off, which is when Google claimed to have achieved a quantum computing milestone and said that it had achieved something called quantum supremacy. And then this was all over the place. In fact, I think that's around the time that people started asking anybody who knew a little bit about quantum computing like me to come and start giving popular lectures on quantum computing and so on, because everybody wanted to know what was happening. If Google is getting into this, and Google has not just gotten into it, but claimed to have achieved quantum supremacy, whatever that is, then this must, maybe it's reality, right? Maybe it's not science fiction anymore. Maybe it's not in the Marvel verse or whichever comic verse that people are talking quantum now. So yeah, so Google put out something in 2019, and much more recently, which is, so I'm just a timeline, if you will. So 2012, we have the Nobel Prize. I think this quote of Serge Haroche is from 2016 or 2017, which is when people started seeing qubits in action. 2019, Google comes out with this quantum supremacy experiment, and this is November 2022. IBM unveils a 433 qubit processor, which is actually accessible to those of us who are a partner with the IBM Quantum Network, and IIT Madras very recently also became a partner in the IBM Quantum Network. So we now indeed have access to machines which have of the order of 400 qubits, right? So that's where we are at today. So some of you may have heard this term, noisy, yeah?
It had triggered a huge debate that whether they have it was a supremacy in the first place. Is what IBM claimed. So now looking back, like that did that claim hold true?
Yeah, so can I come back to this question in the end?
Uh,
Because I'm not sure that everybody, I mean, I think maybe it's better to lay out what potentially could be a quantum advantage. I don't quite like the term supremacy, so I will call this quantum advantage. So what is quantum advantage? Let me tell you a little bit about that, and then
right.
we'll revisit this in the end about whether Google really did demonstrate quantum advantage or not, okay? So often if you read these popular articles and so on, you will find this terminology, noisy intermediate scale quantum devices, or NISQ. So you'll often hear people saying that we are in the NISQ era. So why do we say this? So according to me today, we do not yet have what we like to think of as a universal, fully scalable quantum computer, right? But what we do have are quantum processors or quantum devices of some form. They are indeed very noisy. They are intermediate scale because we are still counting qubits, right? We are not counting terabytes and gigabytes of memory. We are counting qubits, right? So this, for example, is what the Google 72 qubit device looks like. So much of this is just the paraphernalia that goes into supporting the chip which has the quantum processor, which is sitting somewhere deep inside here, okay? So this chip is I think of the order of maybe hundreds of nanometers or a few millimeters or something like that, of that scale, right? Sorry, micrometers, this is what I said, yeah. So maybe 100 nanometers to a micrometer or something. But you see that little chip is sitting somewhere deep inside this big device. Any idea what the rest of it does? Exactly. So the rest of it is just the system to cool this chip down to liquid helium temperatures, which is of the order of 4 Kelvin, not absolute zero. We don't reach absolute zero, of the order of maybe 4 kelvins, right? So that's, and the rest of it is the supporting electronics, the control electronics and so on. So this is the stage we are at. Some of you who have seen the history of computing, this might remind you of the early days of computers itself. If you have seen, I don't know, I forget what the movie, the Turing movie is called, The Imitation Game. Yeah, you've seen this big device that Alan Turing was working with, which had a whole bunch of mechanical switches and knobs and so on, which he actually used to crack the Enigma code, right? So that was your early prototype classical computer. In a sense, this might be that, right? Because just the size and scale of this is just too big for you to even think about this as scaling and becoming sort of one quantum computer in every house kind of thing, right? We are very far away from that. This is another company which, this is their 16 qubit device. This is IBM's Q1. If you go back, they call this Q2, what they have right now. So they are now calling the 400 qubit processor as Q2. It is the next generation of quantum processor that they have unveiled after maybe 7-8 years. The first generation was around 2016, like I said. So this was one of the early prototypes which had 50 qubits. But once again, the chip, the processor itself is sitting somewhere deep inside. These IBM qubits and the Google qubits and the Rigetti qubits are all made up of what are called superconducting qubits. So they heavily rely on the fact that these systems have to be cooled down to very low temperatures, and the physics of how they function is really based on superconducting junctions, what are called Josephson junctions, right? Okay, so this is just the zoomed out picture of what these devices look like today and where we are and so on. But what really is quantum computing, okay? So I'm not sure how many of you here are familiar with, how many from physics background? How many with a physics? Okay, let me ask this a different way. How many of you have maybe taken a course on quantum mechanics? Okay, that's a reasonable number of you. Okay, so maybe a lot of things that I say will be familiar to you, hopefully. So the qubit is of course the quantum bit. How is the quantum bit different from a classical bit, and why should we be interested? Because of superposition. Thank you. Yes. So let's go over this concept a little bit, right? So classical information, as you know, is you talk about manipulating bits, right? A bit mathematically is just a binary valued variable, right? It's a mathematically a field, a binary field, or it's a variable which can take one of two values, 0 and 1, right? That's what your classical bit is. So correspondingly, let's say I write my quantum bits as some 0 and 1, but you see I've now switched to a different notation. I'm now putting this vertical line with a bracket, okay? And this is how I'm going to label my quantum bits. So this is my quantum bit 0, this is my quantum bit 1, okay? But what's different? Is it just the fact that I'm now using some fancy symbols to write the 0 and 1? No, what is different is that these objects, so I will call this as a ket, okay? I will call this as ket 0 and ket 1. The qubit state 0, I will call this as ket 0, and the qubit state 1, I will call this as ket 1. These are no longer just numbers, or these are no longer just a variable. These are, mathematically speaking, they are like vectors. These objects behave like vectors in a vector space, and this is something you're all familiar with. I know this is something that was part of your curriculum also. You've all done basic linear algebra course, so you all know what is a linear vector space. So these objects behave, transform like vectors, right? So the ket 0 and the ket 1, and so I don't know whether I wrote, yeah, okay, so this is what, so let's look at this statement first. So they are actually, so both the ket 0 and ket 1, they belong to a two-dimensional complex linear vector space. And you know by definition that if I take two vectors in a vector space and I make a combination of them like this, right, that is I make an A0 plus B1, where A and B could be complex numbers in general, they need not be real numbers, then the vector that I get out of making this combination is also an element of the vector space, right? That's how you fundamentally define a vector space. You say it's a collection of objects. So first of all, you all know that vectors does not mean your real three-dimensional Euclidean vectors, which one has studied in high school. You've gone beyond that. You go to an abstract object. You go to an abstract collection of objects which has this property that you take any two elements of the set, you make a combination. You could make a real combination. Maybe that's what you've done for the most part in your linear vector space course, right? When you write an A V1 plus B V2, maybe your A and B were real. But now because we are doing this to depict quantum states, you have to go into complex numbers, okay? So these coefficients now can be complex, and then you make a combination of any two elements of this space, you get a third element also of the same space. That is by definition of a vector space. So now my qubit, the states of my qubit are vectors in a vector space. So if I take two basic states like a logical 0 and a logical 1, the set of states that my qubit can access doesn't stop there. The classical bit can only be in state 0 or state 1. But the quantum bit, because it can take any state inside a vector space, it can access not just the 0 logic and the 1 logic, but it can access any such linear combination of 0 and 1. And such a general combination, I will call this as psi. So I will call this as ket psi, okay? And this is what is called a superposition, right? In quantum mechanics, in physics, we refer to this idea of taking linear combinations of valid states and realizing another state, right? This idea is what we call a superposition. So you can take a complex linear combination of 0 and 1, and that's also a valid state of your qubit. Now I have put an additional constraint out here, okay? Now this constraint comes from quantum mechanics, because now this is the mathematics of it, right? The mathematics of the qubit is that it is no longer just a binary valued object. It is an element of a linear vector space. It is a vector in a linear vector space. In particular, it's a vector in a two-dimensional linear vector space. So you all know how you identify the dimensionality of a vector space? Yes? Cardinality of the basis, very good. So how many linearly independent elements do you have in the vector space? So in the case of a qubit, you have exactly two. You have exactly two linearly independent elements, the logical bit value 0 and the logical bit value 1. So it's a two-dimensional complex linear vector space. But now what is the physics of it? Physically, what does this mean? So physically, a qubit corresponds to what we call a two-level quantum system. So let me just write this out. So I will not be able to give you a quantum mechanics primer here, right? But maybe we'll discuss the properties of these quantum systems as we go along when we discuss different properties of the qubit. But I'll give you a very concrete example of what I mean by two-level quantum system very soon. Yeah, before I go to the matrix representation. Okay, so let me just say that physically this corresponds to a two-level quantum system. It simply means any physical system which is small enough that it is truly exploring its quantum nature and whose dimensionality is constrained to be 2. A simple example of this would be something like a spin-half particle. So we all know of electrons, protons, neutrons and so on. In fact, one of the earliest realizations of a qubit was what is called a nuclear spin, right? Of the kind that is used in medical devices like NMR and so on. So a nuclear spin, if you think of a spin-half nucleus, a nucleus which has a residual spin-half, then you know that a spin-half particle, something that one probably studies even in high school, can exist in one of two states. When you apply a certain magnetic field, then your spin-half particle can either align parallel to the field or anti-parallel to the field. So this is what I mean by two states of a physical system. There are two possible states that the physical system can access under some such external constraint. Obviously, these two-level systems don't come for free. You have to put in some physical constraints and then you get a more idealized two-level quantum system. These two-level quantum systems are described by, again, these 2D complex linear vector spaces. So this is the kind of connection between a qubit, a two-dimensional linear vector space, and two-level physical systems or two-level quantum systems. So to make this a little more concrete, we can give a matrix representation to this, right? So I can give an explicit representation to this two-dimensional complex linear vector space, right? So the kind of representation I give is in terms of these arrays, which are called column vectors. I don't know if you ever use this kind of representation in your linear algebra course, but this is, yeah, you did, okay. So this is how you would represent typically a two-dimensional vector space, right? You can represent it as two column vectors. So I pick a particular representation for the 0 logic, which is 1, 0. I pick another representation for the 1 logic, which is 0, 1, okay? And I've picked these column vectors obviously in such a way that they are linearly independent. That is something you can check, that these two vectors are linearly independent. And so an arbitrary state, this ket psi, will have a representation as AB, where A and B are complex numbers. That would be the arbitrary, a general state of a qubit, right? So yeah, I think I'm saying that right below. So yeah, so at the end, I'm also making this connection, which I just mentioned, two-level quantum system, right? So yeah, what is a two-level, yeah, go ahead. Yeah, so I will just come to that. When I describe the physics of the problem, that will maybe, physics of the system will become a little more clear. So before even going into things like nuclear spins and so on, one can talk about a much more simple and very visible example of a two-level quantum system, and that is just polarization states of light, right? So you all know that the light that is being blasted out here is not polarized, right? This is unpolarized light. But if you were to wear a polarizer, a sunglass or something, you know that it's going to filter out certain polarizations, and there's only going to be one residual polarization that your filter typically retains. So what is polarization of light? So what does one mean by polarization of light? Direction of what? Vibration of what? Excellent. Okay, so light is an electromagnetic wave. It's a traveling EM wave, but it's a traveling wave of a particular kind. It's a transverse electromagnetic wave. So what is vibrating is essentially electric and magnetic fields. You can think of it purely in terms of electric fields or in terms of magnetic fields, but you stick to one of them. Then the direction in which these fields can vibrate has to be perpendicular to the direction of propagation. That's what a transverse wave means. The vibration is always perpendicular to the direction of propagation. So now if I fix a certain direction of propagation, I think in this case this is what the direction of propagation is, then you see these are all the different possible polarizations that I can have. I can have the electric or the magnetic field vibrating in this direction. So let me give some names for this. So let me say I call this Z, okay? Then maybe this is X and this is Y. I hope that makes sense. So let me say coming out of this thing is Z for me, and this is X and this is Y. Doesn't matter. Let's say the propagation direction is Z, and so the polarization, the vibration of the electric or the magnetic field has to be restricted to the XY plane like this. And obviously now we are back to like a real two-dimensional plane, except there is also now a complex phase. These electric and magnetic fields can have a complex phase attached to it, right? So one shouldn't get carried away too much and think of this just as a two-dimensional real vector space. It's actually a two-dimensional complex vector space. You can obviously identify two perpendicular directions in this, let's say the X and the Y. So I can call this as vertically polarized. I call the Y as horizontally polarized. So this is horizontally polarized. This is vertically polarized. This in the middle would be, it's a combination of vertical and horizontally polarized. So you can, I sometimes call this 45-degree polarized. Is there a direction that is perpendicular to this? Which is also allowed, right? Which is the 135. So I can do this, right? Sometimes people call this cross polarized. So that is 135, right? So you see some of the mathematics of a two-dimensional linear vector space coming into play here. You have two perpendicular directions. You can either pick vertical, horizontal, or you can rotate and pick 45, 135. That's the basis for you. And any polarization, which is a linear combination of vertical and horizontal, or a linear combination of 45 and 135, is a allowed polarization state, because so long as you're in the XY plane, you're fine. You satisfy the condition of being a transverse electromagnetic wave. So what is your polarizer, your Polaroid filter or whatever, what is it doing? It is basically picking some axis. It's, let's say it's picking the vertical axis, and then it's allowing only vertically polarized light to filter through. So this cuts out a bulk of the light that's coming in, and that's why sunglasses are nice in this weather, right? So you can think in terms of now polarizers, you can think in terms of filters, but this is an example of a qubit system for you right there. And in fact, this was probably the first qubit that was realized in order to demonstrate something called quantum key distribution, which is a quantum communication protocol, a secret quantum communication protocol, or a secure quantum communication protocol. So let's look at this in a little more detail. So yeah, these are all the things I told you already. So the direction of the oscillation of the electric field component specifies the polarization. Light is a transverse EM wave. So now I make this identification. This V, sometimes people call this a ket V, to say that this is one state of the qubit. So the qubit is basically now the polarization states of light, right? The set of states that your qubit can access is these polarization states of light. This is a toy example, right? But it's a toy example which captures all the features of what a quantum bit can and cannot do. So now you identify a logical 0 with, say, the vertically polarized light. You can identify the logical 1 with the horizontally polarized light, and this is the simplest physical example you have of what I called a two-level quantum system. Okay. So this is what I said. You now have your polarization filters, which will allow light of a particular polarization to pass through, which will block light of a particular polarization, and so on. Now, when this happens, so let's say that this is something that's only going to allow horizontally polarized light through, right? What it means is blocking the vertically polarized light. Now, mathematically, this is possible only if these two, the underlying mathematical states, the underlying vectors that describe these two polarization states must be orthogonal. You know what orthogonality is in a standard vector space sense. In this, I suppose you've not seen this ket notation that I'm writing right now. You've not seen this. So in this ket notation, when I write the 0 ket and the 1 ket, in order to define an inner product, okay, what do you do normally? I think you write down something like this, right? If I have two vectors v1, v2, you will write down something like a functional like this to describe the inner product. Now this functional becomes something very simple in this notation, okay? So with the ket vector, I associate something called a bra vector. This is represented like this with the bracket going to the other side, right? So associated with ket 0, I have a bra 0. Associated with ket 1, I have a bra 1. Mathematically, this actually corresponds to a very simple matrix operation. So remember, the ket was a 1, 0 like this. The associated bra vector will be the transpose complex conjugate of this matrix. What's the transpose of the column matrix? It will be a row matrix, and in this case the entries are real, so the complex conjugate doesn't do anything. So you end up, so I started with a 2 cross 1 matrix. When I do the corresponding transpose operation, I get a 1 cross 2, and now you know that I can multiply these two. I can do standard matrix multiplication of these two to get a number. So I can now put the bra and the ket together to get a bracket. That's the origin of the ket and the bra terminology. This notation and this terminology goes back to the physicist Dirac, one of the pioneers of quantum mechanics, quantum field theory, and so on. So this is now a notation that all physicists use, and by extension now all quantum computing scientists also use, okay. So this is how you write down an inner product, right? What you would write down as a functional here, I don't know whether you've heard of dual spaces and so on. You take a dual associated with a vector space. So this, taking the transpose and the complex conjugate is like going to the dual space, and then you take an element of the dual and the original vector space, you put it together, you basically have done matrix transposition. So you now are dimensionally matched. So let's do this inner product, right? So what is the bra 0? That is a 2 cross 1 row vector like this. The ket 1 is a, did I say that right? Sorry, this is a 1 cross 2, yeah, I was wondering what I said, yeah. So this is a 1 cross 2 matrix, right? And then I have the 2 cross 1 matrix, right? So I can just do standard matrix multiplication, which is just entry wise. So what do I get? 0, which is the way it should be, because these are a pair of orthogonal vectors in the vector space. So physically, coming back to the physical example now, it's very intuitive that vertical and horizontally polarized states must be orthogonal. They are essentially vibrations along perpendicular directions in a real space, right? So this property, so you can now go back and forth. You can go back and forth between the physical states of light, polarization states of light, and the logical states of the qubit, right? And we now pretty much have all the mechanics to do this. You have identified a representation for the vector space. You have identified a way to do inner product. You have to go from the column vector to the row vector and then put them together to get the inner product. You have a notion of what it means when that things are orthogonal. So you can identify a basis based on orthogonality, right? So this is sort of the correspondence. Yeah, go ahead. Yeah. That's a good question. So this also goes back to what someone was asking about this, why do we need the mod A squared plus mod B squared? So what does that physically correspond to, right? So now, okay, so this is actually this statement, that's why this statement was put here to explain this orthogonality business. So now you see, if I get light of a particular polarization, I don't know what polarization it is, okay? But I need to identify what polarization it is. You imagine, right? You're writing something on your computer, you're putting you encode something, right? You write some code. Now, when you want to read out from this, your device should be able to identify what is a 0 and what is a 1. In terms of light, I have to be able to identify, or my quantum computer should be able to identify what is vertically polarized and what is horizontally polarized. How do we do this for quantum states? We do something called a measurement, okay? Now, classically or normally, if I have to say, a measurement is not something which one really talks about, because yeah, I can measure the length of this box, I can measure the width of this box, and nothing about the box changes. I have an instrument, I have an apparatus that measures the property that I need, and the property itself doesn't change. But that's not the case with quantum states. And this light example really exemplifies that. Because let's say the light that is coming in is a 50-50 mixture of vertical and horizontal polarized. So it's actually the 45-degree polarized. But now if I try to measure and ask, is the light vertical or horizontally polarized? I have to put a filter. That's the only way I can measure. So I put a vertical filter. It obviously filters out 50% of the light and sends something across. Do I conclude that the light is vertically polarized? I put a horizontal filter. Again, it filters out 50% and I get. So unless I actually put a 45-135 filter, in which case the 45 filter is going to allow everything to come through. The 135 filter is going to completely block the light, and that is how I find out that the light is 45 or 135 degree polarized. But you see, in doing so, in putting whatever filter it is that I have put to measure the polarization of light, I have ended up changing the state, except in one case where I had exactly the 45 degree filter and the light that was coming in was also 45 degree polarized, okay? So typically a quantum measurement will modify the state of the system. A stronger statement that we often make is that it destroys the state of the system. Maybe a better statement to make is that it disturbs the state of the system. It is not possible to extract information from a quantum system without disturbing its state. So now when you have to measure, you realize that these filters you can only put along perpendicular directions. So that's where the orthogonality constraint comes in. When I have to read out from a quantum device, I can only read out along these kind of orthogonal directions of the vector space. Physical example is vertical, horizontal, but even if you go into things like spins or superconducting qubits, the same property holds. You can only read out along perpendicular directions. You can only distinguish between perpendicular directions. What do I mean by that? So let's play a game where you prepare light which can either be 45 polarized or vertically polarized, and it's my job to identify which it is. Now you see I'm stuck because you have picked two states not from the same basis. Horizontal vertical is one basis. Since you all know vector spaces, I'm talking the language of basis. 45 135 is a different basis. If I had to distinguish between vertical and horizontal, I can do that by putting appropriate filters. But to distinguish between 45 and horizontal or 45 and vertical, now that is hard because 45 is like this and vertical is like this. So if I put a vertical filter, I'm still going to get 50% of the light even if it is 45 degree polarized. If I put a 45 or a 135 filter, I'm still going to get some light through because these have components. The vertical polarization has a 45 component. It has a 135 component. The 45 polarized light has a vertical and a horizontal component. So these are called non-orthogonal states. So you cannot distinguish non-orthogonal quantum states. There is no measurement which can perfectly distinguish non-orthogonal quantum states. Now these are all unique features of the quantum bit. You don't have a classical analog of this. In the classical case, in some sense, you have only orthogonal states. You have only states like 0 and 1, which you can always perfectly distinguish. You never confuse between a 0 and 1. They are well separated electronic levels in your in a transistor, or you have different ways of realizing what a 0 and a 1 is, but they are well distinguishable physical states. But once you start allowing superposition, once you start allowing things like 45, 135 and so on, you end up with states which can no longer be distinguished perfectly. And that is why this idea of orthogonality becomes important. Because if I have to read out from a quantum computer, I can only do so along perpendicular or orthogonal directions of the vector space. So let's proceed. So these are all things that I told you. Horizontal, vertical can be distinguished. 45, 135, again two perpendicular directions, they can be distinguished, right, because they are like this. But if I do this, so these states I hadn't written down yet. So so you remember in the earlier slide I had said that 0 is vertically polarized, right? And sorry, 1 is horizontally polarized. So what is 45-degree polarized? It is an equal combination of 0 and 1. And now you see the importance of these A and B terms coming in. So remember we said an arbitrary state is of the form A0 plus B1. What is the A and the B? If you think in terms of polarization, it tells you what fraction of your light is vertical, comes from vertical, and what fraction comes from horizontal, or how much of the light that's coming in has a vertical component and how much of it has a horizontal component. But now you know that when I take the sum of those two components, I must get the whole light. I must get the full intensity, right? So the total intensity will have to be split between the vertical and the horizontal, or between 45 and 135. Quantum mechanically speaking, we call these as probabilities. What is the probability that if you send 45-degree polarized light through a vertical filter, what is the intensity of light that will come through? 50%. So what is the probability that you will see light coming through? 50%. So these, it's not the A and the B. The A and B, like I said, can be complex. So it's the mod A squared and the mod B squared. They are actually probabilities. And the conservation of probabilities tells me that the sum of these two things must always be 1. So that is where that constraint came in the previous slide, where I said the general state of a qubit is of the form A0 plus B1 with mod A squared plus mod B squared being 1. It always has to be 1 because the physics of the system tells us that the mod A squared and the mod B squared are probabilities. They are actually measurement probabilities for an arbitrary state to be found in bit value 0 or in bit value 1, and because they are probabilities, they have to sum to 1. So a state of a qubit cannot be any vector in the two-dimensional vector space. It can only be what are called normalized vectors, because this property that mod A squared plus mod B squared is 1 is basically saying that the length of the vector must be 1, or the norm of the vector must be 1. So these are essentially normalized vectors of the two-dimensional linear vector space. So now we have, yeah. 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 Yeah, so I don't think I'm an expert on the Copenhagen interpretation or any other interpretation of quantum mechanics. Let's say that I choose to take an operational interpretation of quantum mechanics, okay, which is what can I do and what can I not do, okay. So clearly this example tells me that I can associate definite states with these orthogonal directions because I can always measure in them. Before measurement, what was the state of the system? Obviously, I don't have a handle on that. It could have been in any superposition. But what can I extract from this system? I can extract measurement probabilities. So this game that I said, where you send me 45-degree versus vertical polarized, that's why I can never win the game. Because I cannot, using a measurement, decide whether what you sent me was 45 or vertically polarized, right? But what one can do is devise measurement strategies such that I win a certain fraction of the time. And there are ways to do that. That's an interesting problem in quantum information theory. How well can you distinguish these superposed states, right? So there is still some information you can extract from it. So let's say that I don't actually worry about what is the system actually doing. So I don't ask, like Einstein did, whether the moon still exists if I don't look at it. No, I look at the moon. If it exists, I say it exists, okay? And if it's a half moon, I say it's a half moon. If it's a Chaudhary ka chand, I say it's Chaudhary ka chand. So I go by an operational interpretation of quantum mechanics. No, those questions are interesting. Yeah, go on. So, well, the way I see it, even with the current, let's say this operational measurement theory that I'm talking about, even there, I don't think experimentally we are really able to do these high precision measurements yet. Now, the kind of questions that Einstein and Bohr and so on were asking goes one level deeper. Basically, what they were trying to ask is whether this 50-50, this probabilistic thing nature that is emerging as we are discussing this, is it truly probabilistic, or is there some underlying process which we don't have access to, which is now in the phrasing of the question itself, you see, it is hard to devise an experiment which can even test that, right? So the best that people try to do is to come up with what are called Bell inequalities, Bell CHSH inequalities, all of those, the Nobel Prize of last year, all of that in some sense is a result of asking these questions. But nowhere has one even been able to go beyond this, what I call this operational interpretation. So while those are good questions to understand the nature of reality, to understand really the nature of quantum systems, I am skeptical if it is actually going to have any benefits, or in the sense if that is something which can actually be measured or verified or falsified experimentally. So people have attempted to come up with falsifiable statements, verifiable statements, and the Bell test was one such, right? But it kind of conclusively showed that physics is non-local, right? And that basically, yeah, so I mean, anyway, so this is a debate that we can have later, but my own sense is that beyond, at least going by the current level of experimental technologies that we have, I don't think those kind of questions can be answered at this point, right? And they will at best be theoretical models that you can work out, right? Okay. So yeah, so this kind of summarizes everything I've said so far. Any other questions on qubits, superposition, probabilities, and so on? So by now it's clear that the quantum bit is a very different object than the classical bit. It's not just about putting kets around 0 and 1. They behave fundamentally differently because of two reasons. One, they are vectors in a vector space. Two, they are subject to the laws of quantum mechanics, which means they're subject to the laws of quantum measurement, which means that you cannot distinguish non-orthogonal states, you can only distinguish orthogonal states, and so on and so forth, right? Maybe I was just doing this last point here. Yeah, so this is just how you would represent the 45 and the 135 polarized light in this notation that I wrote down, right? And for obvious reasons, we call the 45 polarized light as the plus state and the 135 polarized light as the minus state, okay? So this, maybe I'll just skip through this because I'm also running short of time. This is just a way to reparameterize the qubit, and this is maybe something that my students will show you. You plan to show the Bloch sphere? Yeah. Okay. So this is just to show you how you can visualize the qubit in a geometric way. There's a very nice geometric way of visualizing the qubit because you have these. So how do I describe an arbitrary state of a qubit, like 45-degree polarization? How do I describe it? You will say, well, it is the state which has the 1 over root 2 and the 1 over root 2 as the coefficients, right? That's what we saw here. You have this 1 over root 2 and 1 over root 2 coefficients here, right? So by describing the A and the B, I describe different states of my qubit. Different A's and B's will describe different states of the qubit. But now A and B are complex. So for every complex number, I need 2 real numbers to describe the state. So then how many real numbers do I need to describe the state of a qubit? Looks like I need 4, but then I have a constraint which comes from the conservation of probabilities, which is that mod A squared plus mod B squared should be 1. 6? Why 6? There's just A and B, 2 complex numbers. But that is taken care of by the phase, right? So when I say A is a complex number, I write it as mod A e to the I some phi sub A. B I will write as mod B e to the I phi sub B, right? That's how I will represent a complex number in terms of its amplitude and phase. And the phase will take care of negative, positive, all of that, right? I can put a phase of, I can always rotate by pi to get a negative sign, right? So I seem to need 4 numbers. There's a mod A, mod B, a phi A and a phi B. But there's a constraint that mod A and mod B have to satisfy. And this constraint actually reminds us of some trigonometric functions. It reminds us of cosine squared and sine squared in particular. So then I will actually parameterize my qubit like this. I will say it's cos theta by 2 ket 0 plus e to the I phi sine theta by 2 ket 1. So I have an angle theta. There's a reason why I take a half angle. So I say theta goes from 0 to pi, okay? So the identification I have to make is that mod A is like cos theta by 2 and mod B is sine theta by 2. So because they're squared to 1, right? The sum of the squares is 1. And then, but then what happened to the 2 phases? I had written 2 phases here, no? So I had written a e to the I phi A and an e to the I phi B. But here I have just written an e to the I phi. How did I get there? So, which 0 and 1 are orthogonal, but they could still, these coefficients can always carry arbitrary phases like this, right? There could have been a phi A and a phi B here. So what I've done is I've taken this e to the phi A out, okay? So I've then put a bracket here, and then this phase is actually e to the I phi B minus phi A. I can do that. But then what happened to this e to the I phi A which was sitting outside? I have not written it here. The reason I have not written it here is because physically that is not an observable quantity. So there are the 2 phases which I associate with A and B. I can instead think of them as a global phase or an overall phase, which is what the e to the phi A sitting outside is, and the difference between the 2 phases is what I call a relative phase. Now in physics, you can never measure an absolute phase. You can always measure phase differences. So this is what is called a relative phase. So this single phase factor that I have sitting here is basically the relative phase between qubit 0 and qubit 1. This overall phase doesn't matter. Doesn't matter, it could be anything, but it is not something that I can distinguish from. So I cannot say distinguish between I0, 0, plus 0, minus 0. They're all the same states as far as my quantum device is concerned. So that's what I mean by an overall phase. But a relative phase, which means whether I have a 0 plus 1 by root 2 or a 0 minus 1 by root 2, they are two different states. In fact, one is that 45-degree state and the other is a 135-degree state. They are perpendicular states. So they are very much distinguishable states. So this difference comes through the relative phase. So there is an e to the I phi, where the phi is 0 here, and there is an e to the I phi. What's the value of phi here for the minus state? Pi. Phi is pi here. So that's why there's a relative phase of minus. So the relative phase matters, absolute phase doesn't matter. So putting all this together, I end up with this representation of a qubit in terms of just two angles, one which represents the amplitudes, the modulus squareds, the modulus A and the modulus B, and the other which represents the relative phase between the two qubits. So these are the two angles that I need to describe a general quantum state. Now these angles might remind you of something. Theta going from 0 to pi, phi going from 0 to 2 pi. It describes a certain geometric symmetry. What geometry does it describe? If I sweep one angle from 0 to pi in a three-dimensional space and another angle from, it describes a sphere. And because the radius in this case is essentially 1, because the modulus squared of these two is 1, this describes a unit sphere in real three-dimensional space. So there's a one-to-one mapping between the states of a qubit and the points on the surface of a sphere. So I think I've put this picture here. So this is what's called a Bloch sphere. Those of you who may have logged into IBM, how many of you have logged into IBM Q? And okay, so few of you. Okay, so you may have seen there this Bloch sphere visualization, right? So that's what this is. So it's a one-to-one mapping between, so every point on the surface of the sphere is a valid state for my quantum bit. Conversely, every state of my quantum bit can be mapped to a point on the surface of the sphere. And now one can sort of describe the quantum advantage in a very dramatic fashion. You can say that the classical bit is essentially constrained to be at the north and the south pole of the sphere, whereas the quantum bit can now access all the points on the surface of the sphere. So you've gone from being able to access just 2 points to an infinity of points, because you've gone from classical to quantum systems, you've gone from binary fields to two-dimensional linear vector spaces. So you can access all the points on the surface of the sphere. That's great, that's quantum advantage, but you can only measure along perpendicular directions. And if you notice, I have marked these perpendicular directions here. They will always come along opposite points of the sphere, antipodal points, the ends of a diameter. So this I leave it to you as an exercise to work out. Those of you who haven't seen this, where does the plus and the minus lie? Okay, I think I've made a mistake here. I don't know why my plus is gone there and my minus has come here. So I think this should be the plus and this should be the minus. Okay. So you can now work out. So if this is the vertical polarized state and this is the horizontal polarized state, then you can work out that, so they are on the, let's say that this is the z axis, this is x and this is y. So if the vertical and horizontal polarized states are on the z axis, then the plus and minus, the 45, 135 states are actually on the xy plane. In fact, they are the two endpoints of where the x axis cuts the diameter. So you can pick opposite points where of the diameter and they will turn out to be orthogonal states. So you can only measure along orthogonal states, but your device can access all possible states mirroring all points on the surface of the sphere. So this is where truly the power of computing with a quantum bit really comes from. Okay. So I've written out these things. Maybe I can share the slides with you later for you to work out. And this is something that my student will show you on the IBM platform very soon. So this is all some detail. So I think I have gone into some detail talking about non-orthogonality and distinguishability already. So let me just quickly go through this. I've already told you how the vertical and 45 degrees cannot be perfectly distinguished. So the sphere in some sense shows you the power of the qubit. But now you have to sort of come to reality and say what is really possible and not possible with the qubit, right? And this kind of telling you what's not possible. You can access all the points on the surface of the sphere, doesn't mean you can distinguish all the points on the surface of the sphere. You can only distinguish specific points which are the ends of the diameter, probabilities, etc. So I just want to mention one name here, that's Heisenberg and his uncertainty principle. And this is where the uncertainty principle actually comes in. It tells you that you can't measure a given system, you can't measure multiple properties of a given system accurately simultaneously, right? So this is how many of you may have heard of the uncertainty principle. You can't measure position and momentum of a particle simultaneously and accurately. How does it translate to whatever we've been discussing so far? So we discussed two different bases. We discussed the horizontal vertical, the 0, 1, and we discussed the 45, 135, which is the plus and the minus. So this is the example that I gave you. I can either measure in the 0, 1 basis and I can identify horizontal versus vertical, or I can measure in the 45, 135 basis and I can distinguish between 45 and 135. But I can't simultaneously do both. And if I do one of those measurements, I have already altered the state of the system, and so I can't make any further measurement. It's not going to yield any information. So this is at the heart of the uncertainty principle. You can't simultaneously measure different properties of the system. Yeah. 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 So I don't know what you mean by a view and so on. So in this case, one is not talking about any property of light. One is talking about a specific property, which is polarization. And the way you can detect or identify polarization is by putting another object which has a particular axis of polarization, right? And the axis of polarization of the incoming light interacts with the axis of polarization of the object, and you get an outcome, right? So once that interaction has happened, you have already altered the polarization state of the incoming light. So you can do subsequent measurements. I'm not saying that you can't, but that's not a probe of the original state. You've already modified the state. Okay, I hope that answers your question. And that also is how you do quantum measurement in general. You have to interact your system with a measuring device, with an instrument. And in the process of that interaction, the state has already altered. So the way your IBM quantum computer will actually do measurements, and this is something again my student will show, is you prepare the same state. You prepare the same state 1,000 times, 2,000 times, and you repeat the same measurement. This is like I give you a coin and I say find out, is it a fair coin or a biased coin? Is it something I can use for tomorrow's IPL final, or is it something that is rigged? So the point is, when you toss, you only get one outcome. You can't decide based on that outcome whether it's a fair coin or a biased coin, or if there's a bias, what is the bias? You will have to toss it 1,000 times before you can say with some degree of confidence that it's a fair coin or a biased coin, and if it's a biased coin, it has so much bias. So you have to get measurement statistics. Only by getting the statistics out can you get the probability distribution. So any quantum process that you run on these quantum devices is typically going to be a multi-shot process. It's not a single shot. It will always be, so you will see when you run a program on IBM Q, it will say how many shots. So you will have to specify that you run it 1,000 shots, 2,000 shots. I think my student has run things for 10,000 shots. It depends on what confidence you want, what accuracy you want your outcome to be with, right? Okay, question, there was one, yeah. Yeah, so Schrodinger's cat is basically an example of what we've been calling superposition, right? So Schrodinger's cat is basically a very extreme example of what will happen if you take a macroscopic object like a cat and throw it into a superposed state, okay? So you imagine that you put this cat in a box, and I think it's a kind of bizarre experiment. You have some radioactive something detonating inside, I think. So with some probability the cat is either dead or alive, but the act of measurement is like opening the box essentially. Now your cat, although it can exist apparently in a superposition of being dead or alive, ultimately when the answer to your question has to be either dead or alive. That's like saying the answer to my coin toss is either head or tail. There's nothing in between. But the system can exist in intermediate states. That's what you've seen even with polarization. But the answer will always be vertical or horizontal, 45 or 135. So the answer is like a collapse. That's what people call a collapse sometimes. But the system could be in a superposition, but the readout will collapse into one or the other. Yeah. 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 Mm. Mm. Good. Yeah. See, I'm a good advertisement for quantum computing because I tell you all the negative things, but then I'll show you what you can do despite all these drawbacks, okay? So, yeah, because I think it's important to understand that this is not magic, this is not some super powerful thing that's happening. Well, it's physics, it's very, very interesting, fascinating physics of a particular kind, which leads to a new computing model. But the point is, it's a completely new computing model. So, you have to think about it very differently, right? It gives you this power of superposition, but you can only read out in a particular way. So let me give you an example of a task, and maybe this is where I will hopefully finish soon by giving you an example of a task where you can still achieve speed up, although you can only measure in along specific directions, right, along orthogonal directions. So in a sense, your interface is the classical world because you can only read out into orthogonal states, which I said are like classical states. So you're always interfacing with the classical world, but the device itself is quantum. Okay, so that is where the speed up or the advantage has to be leveraged in a clever fashion. Okay, so let me go over some of these things quickly. Yeah, I hope there's time for some demonstration at least. Okay, so yeah, so I've just so far described the qubit, but now how do I do computations, right? So far I've only shown you the landscape of the qubit. I've not shown you how you can compute with it. So how do you compute? You need logic gates, right? So you need your equivalent thing for your NOT, AND, NOR, etc. So the NOT gate is very simple. It's something which takes 0 to 1, 1 to 0. So quantumly what has to happen? It has to take my ket 0 to ket 1 and ket 1 to ket 0. But classically, or in your standard computational paradigm, how do you transform, how do you compute using your classical bits? You implement what are called Boolean functions, right? Functions which take binary valued variables to binary valued variables. What does a quantum computer do? It has to map vectors to vectors. It has to map objects like this, right? So what is this transformation actually? It has to take AB to what? BA. So what kind of mathematical object will take vectors to vectors? Transpose will give me a number, no? But I have to get a vector. Will still give me a number. So this is a 2 cross 1 has to be mapped to a 2 cross 1. So in a real vector space, how do I rotate? Using matrices. So I need a 2 cross 2 matrix here, so that when I do this matrix operation, I again end up with a 2 cross 1. And of course, you can work out maybe that this matrix has to be this. Okay, so quantum gates are essentially matrices. They are 2 cross 2 matrices if you're working with qubits. Sometimes you can think about working with higher dimensional systems. So beyond binary logic, you can go to ternary, quaternary, etc. So then correspondingly the matrix will be size 3 by 3, 4 by 4, whatever is the dimension of the system that you're working with. For qubits, these are just 2 cross 2 matrices. So quantum gates are 2 cross 2 matrices. But will any 2 cross 2 matrix do? The answer is no, because you still have to satisfy this condition that mod A squared plus mod B squared is 1. Now with the NOT gate, that is automatically satisfied. You've gone from AB to BA, okay? But in general, you have to satisfy this constraint because you have to conserve probabilities, okay? So now is where the physics comes in again. So because you have to have this conservation of probabilities, not all matrices are quantum gates, but a special class of matrices called unitary matrices are quantum gates. So have you heard of unitary matrices? Some of you have. A unitary matrix is one whose complex conjugate transpose, when you multiply, gives you identity, okay? This is important because these are matrices that preserve the length of a vector. When I act a unitary matrix on a vector, I get another vector whose length is the same as the length of the first vector. Length meaning the norm, the mod A squared and plus the mod B squared is always preserved. This is what you need in order to transform valid qubit states to valid qubit states, okay? So this we have already seen. So any 2 cross 2 matrix that preserves this length, these probabilities, is a valid quantum gate, and these are unitary matrices, a special class of matrices, essentially with this property that U times U transpose complex conjugate is identity. The other way around, U transpose complex conjugate times U is also identity. Such matrices are called unitary matrices. You can check that this property holds for this NOT gate that we've identified. But now again you see the difference. In the classical case, what are all the single bit gates that you know? Gates that take you from a single bit to a single bit. There's just one, which is the NOT gate. But you look at the quantum case now, what are all the single qubit gates? This is the NOT gate. That's not the only gate, because we just said any 2 cross 2 matrix which preserves the length of the vector is a valid quantum gate. And once again, there's an infinity of them. So there's an infinity of single qubit quantum gates that one can construct, okay? So this again opens up a new space for you, right? You've gone from having a single Boolean function. A single bit Boolean function is just one, but a single qubit gate, there's an infinity of them. There's a whole class of them called unitary matrices, okay? Now, classical computing essentially runs on 2-bit gates, right? The most important gates are the so-called universal gates, right? The NAND and the NOR and so on. So what is the quantum analog of that? So you have 2 qubit gates. So let me just explain one 2 qubit gate out here. So this is how I would represent a very rudimentary quantum circuit, okay? There are 2 registers, 2 qubit registers. I've simply labeled this as X and Y, 2 output registers, and this is the gate, okay? Now the earlier gate that I wrote down, I will represent like this. Let's say the NOT gate, right? I'll call it the X gate. So this is how I'll represent a single qubit gate. But now this is a 2 qubit gate. So you see they're connected, because these 2 qubits have to be coupled physically in some way for you to actually get a 2 qubit operation. What is the 2 qubit operation that we are realizing here? It's called a quantum XOR gate. It's more commonly called a controlled NOT gate. You see what's happening is the first register remains the same at the end, but the second register is getting XORed with the first register. And you'll realize that basically depending on whether the first register is 0 or 1, so if the first register was 0, Y XOR 0 is always Y. So the second register remains unchanged. But if the first register were 1, then Y XOR 1 is Y complement. So the second register is actually getting flipped. So this is a gate where the second register gets flipped depending on the state of the first register. So that's why it's called a controlled NOT operation, right? It's the second qubit, the state of the second qubit is controlled by the state of the first qubit. So this is called a control bit, this is called a target bit, and this is a very important 2-qubit gate which you will have to encounter in any circuit that you run on a quantum device, right? Now this is again just one example of a 2-qubit gate. There is again an infinity of them and so on. But it turns out that for universal quantum computing, it suffices to actually realize just one 2-qubit gate. Almost like the classical case where you just say that NAND gate is enough or the NOR gate is enough to realize any Boolean function. Here, one 2-qubit gate has to be realized. The C0 is what is realized in most architectures today, and a bunch of single qubit gates. So this you will see on the IBM interface when one of my students demonstrates this. This is a matrix representation and so on, but I'll move on. And so this is the universality statement that I just made. Any multi-qubit logic gate can be implemented simply using this 2-qubit gate, the controlled NOT gate, and single qubit gates. Okay, so this is how one goes about computing, implementing gates on qubits. So now can we put the gates and the circuits together to realize a speed up? So this is what someone asked me. Yeah, you had a question? So how do you get a speed up from a quantum computer, or why do you get a speed up, right? So the answer goes back to what people called in the 90s quantum parallelism, right? The idea, so what does superposition gain you? What does going from just 2 points on the Bloch sphere to the entire surface of the Bloch sphere gain you? It gains you this notion of parallelism. So instead of evaluating a function just at bit value 0 or at bit value 1 or a specific bit value, I can now prepare a superposition and evaluate the function in a sense simultaneously at bit value 0 and 1. Because when my state is in a superposition of 0 and 1, all the logic gates that I apply, they're all linear. The whole thing is a linear system, right? So all these gates are getting applied simultaneously to 0 and to 1. So if I build a quantum circuit here filled with many gates and many whatever C0s and single qubit gates and so on, if the input is in a superposition, this entire set of operations is simultaneously being done on all the individual states of the superposition. Unlike a classical case where if I have to evaluate a function for 0 and 1, I have to do this serially. I have to say first do f of 0, then do f of 1. If I have to parallelize, I have to have access to GPUs where I parallelly send this information, but still there are distinct devices evaluating bit value 0 and bit value 1. But here I have a scenario now where I can simultaneously evaluate both bit value 0 and bit value 1. So this is what's called quantum parallelism, that in a sense you are able to evaluate many different values of the input simultaneously, right? So let's take a simple example, some single bit Boolean function. So here's an example of a circuit that's actually going to do this. But before I do this, I want to show a toy problem. Yeah, so this is what I want to talk about. Maybe we'll go back to the circuit if necessary, but let me just talk about this problem and conclude with this. So this is David Deutsch, physicist, who actually came up with the first example of a quantum speed up, right? So this is the problem. So there are two people playing this game, Anita and Bharat. Anita selects a number from 0 to 2 to the n minus 1. Why have I made this strange thing, 0 to 2 to the n minus 1? Basically, I'm looking at all numbers which can be represented as n-bit strings. In binary, when I represent these numbers from 0, so let me call this some capital N, 0 to capital N. This is a set of numbers which in binary can be represented using a bit strings of length up to n, okay? Maybe I'll tell you a simpler version of this. Let's say that she selects one of two numbers, 0 or 1, okay? And she sends it to B. B evaluates a function on 0, 1 Now it's a Boolean function, so the outcome is 0 or 1, okay, and sends the outcome. Now if it's a single bit function, what happens? So let's take the simpler case of this quantum speed up problem. Let's say it's a single bit function f of x. Now I have f of 0 and I have f of 1, just two values to be evaluated, right? Now f of 0 can either be equal to f of 1 or f of 0 will not be equal to f of 1, because you have only two possible outcomes, right? They both be 0 or both be 1, or one is 0 and the other is 1. So now the question that B is asking A is, can you tell me whether this function is of this type or this type? I don't want to know the answer to whether what is f of 0 and what is f of 1. I don't need you to tell me that, but I need you to tell me whether the function is constant. Constant means f of 0 is the same as f of 1, or whether it is balanced. Balanced because half the time the outcome is 0, the other half of the time the outcome is 1, right? So balanced. So is the function constant or balanced? So how will a classical device do this? So let's say A has only a classical calculator. So A will punch in f of 0, evaluate that, punch in f of 1, evaluate that, then compare the two. Is f of 0 same or different? Now based on everything I have told you, you already realized that a quantum computer, if A had a quantum access to IBM Q, then what A would do is prepare a superposition of 0 and 1, evaluate the superposition, but then what? So is it possible that after evaluating the superposition, A is able to somehow make a clever measurement which tells her whether f of 0 is the same as f of 1 or not? So far what we've seen, the device is capable of doing this, right? Because the device can apply, your f function will translate to some circuit, some set of gates. A can prepare a superposition. That's like preparing the 45-degree state or the 135-degree state. You input that superposition state to your device. It performs the computation. All of this is happening in parallel. But this is where the challenge of designing a quantum algorithm comes. Is it possible now to get the outcome in such a way that you can in one shot, without having to do two times? If you again have to query it twice, then you have no speed up over the classical case. In the classical case, you have to compute twice. You have to compute f of 0 first and then f of 1. So without having to compute twice in a single shot, can you get the answer to this question of whether f of 0 is the same as f of 1 or not? So what Deutsch showed is that it is possible, and the answer actually lies in this interesting thing called the relative phase, which we already encountered. So the trick is to do a series of manipulations such that this information about whether f of 0 is the same as f of 1 or not becomes encoded in the relative phase between the 0 and the 1. And as you know, in one case, if the relative phase is plus versus the other case the relative phase is minus, you can do a measurement and distinguish these two states. So that's exactly what happens in this Deutsch algorithm. What I've written on this slide is a more dramatic version of the speed up. The speed up that I just kind of explained is going from two evaluations to a single evaluation. So in computer science, this is called a query model. How many times do I have to query my device? You think of your device as this all-knowing, all-powerful being, which is called an oracle, and you keep asking questions to the oracle and the oracle will keep answering it, right? How many questions do I have to ask the oracle before I get the answer to my question? Classically, for this problem, I need to ask my oracle two questions. I have to say, what is f of 0? What is f of 1? And then I compare. The oracle is is a device which can compute this f. Quantumly, if I have an oracle that computes f, I need to only query the oracle once. That's what Deutsch showed with his Deutsch algorithm. Now, what I have on this slide is a case where I do this not for a single bit function, but for an n-bit function. So now I have not just two possible inputs, but 2 to the n possible inputs. Because think of all possible n-bit strings, okay? And now you're given a promise. You're given a promise that the function is either constant or balanced. Constant means it's the same for all values of x. Now x can take 2 to the n possible values, right? All possible n bit strings. And balanced means for half of the strings the output is 0, for half of the strings the output is 1. Classically, how many times now do I have to query? Classically, 2 raised to, not 2 raised to n. I can do something slightly clever than that. I don't need to query all the strings, right? Let's say I query half. 2 raised to n by 2 plus 1. Okay? So think about it. You will have to query the classical device 2 raised to n by 2 plus 1 times, okay, which is still exponential in the size of the bit string. But quantumly, what Deutsch and another computer scientist by name Jozsa, Richard Jozsa, showed is you need to only query once. Because it doesn't matter whether it's a single bit function or an n bit function, you prepare a superposition again. You can again prepare a superposition of as many states as you want. Again, you encode this information in a relative phase and you do one measurement. You run the circuit once, you do one measurement, you get the outcome. That will tell you whether the function is constant or balanced. So this is what is called an exponential speed up. You've gone from requiring something like 2 to the n by 2 plus 1 queries to a fixed number, that's just one query. Okay, so this maybe answers the question of you can only measure in particular ways, but still you can achieve speed up by exploiting the power of superposition and this additional phase degree of freedom that you have. Yeah. Yeah, exactly. You would require n qubits, but that's the same thing with the classical case also. You need an n bit, it's an n bit Boolean function, yeah. The one thing you need actually is an additional ancillary qubit, okay. So maybe, I don't know if we have time to show the full algorithm here, yeah. So in this case, there's no accuracy issue, right? Because that's what I said. Your goal is not to evaluate the value of the function itself, okay? Because in that case, you can only do this probabilistically because you have to measure. You can only measure in 0 or 1. But your goal is to find out whether f of 0 is the same as f of 1 or not. And that information, if you put it in a phase, then in a single shot measurement, you can 100% get the answer of whether f of 0 is equal to f of 1 or f of 0 is not equal to f of 1. So it's a cleverly posed problem which says that you can achieve speed up in the quantum case provided the property that you're investigating is what we call a global property of the function and not a local property. Because a local property, you again have to keep measuring each qubit in that local basis, and then you kind of lose out on this advantage that you had. But because it's a global property, you're able to do this accurately in a single shot. Because I skipped the details of this algorithm and so on, it's kind of what I said, and I think I have a circuit and all that, but maybe let me skip all of this. Actually, I will kind of go to, yeah, so this is just to say what a quantum computer can do. This, all of you know, quantum computers can search quadratically faster, they can factor numbers exponentially faster, and this is the original reason that people got interested in quantum computers, because it could solve the prime factorization problem exponentially faster than the best known classical algorithm and so on, right? So you already see there are two kinds of speed ups. There is an exponential speed up like the Deutsch problem that I mentioned, or this factoring problem, or there could be quadratic speed ups like the search problem, okay? But I think I will now skip all the way to the end. Yeah, just to show you where we are at. So this is IBM's quantum roadmap, okay? So all the green ticks is what has been achieved. So we are in 2023, and sort of as promised, they unveiled the 433 qubit machine November last year. So the goal now is to go on to 1000 qubits, okay, in 2023. and from 2025 and beyond to actually go to 5K, 10K qubits, right? And so because the power in this paradigm relies on this exponential space that you have, more the number of qubits, obviously larger and larger problems that you can solve on these devices. Just one final thought, why is it taking us so long to build these devices? So I've maybe shown you a glimpse of the advantage and the power of these devices. But why are we still counting qubits? Why are we at 433? Why are we at 1000 and so on? The reason lies in the fact that these are very, very complex systems to control. A single quantum system is anything unlike a cat, anything unlike the famous Schrodinger cat, right? It's a microscopic object. Typically, these polarization states of light, that example I gave you, you almost never use them for computing because they're very fragile. If I prepare a vertically polarized state of light, very soon it is going to depolarize, which means all other polarizations will interfere. It's hard to maintain the state of this polarization, and that's actually a very fragile qubit. These superconducting qubits are much more robust, but still their lifetimes today are only of the order of hundreds of microseconds, maybe at best, microseconds at best. So how many gate operations can you do on this qubit within a microsecond before it loses its coherence, before it kind of all the information in that state is lost? So that is what limits us today. These qubits are noisy, they are fragile, they are hard to control. But then again, 10 years ago, 2013, no one thought we were going to see 400 qubit machines and 1000 qubit machines. But today this very much seems a reality. How much is it going to scale? How accurate is it going to become, in the sense, in terms of noise I'm talking about? These are questions which are up in the air. But this also means there's a lot of challenges, a lot of interesting problems to look at, both from the theoretical side and from the practical side, from an engineering point of view, from a computer science point of view, from a physics point of view, from a mathematics point of view. So this is a field which is truly interdisciplinary in that sense. Just want to conclude by talking about, okay, this is just a tech industry perspective on this, on what's the kind of investment that people have been putting into quantum computing these days, and you see things growing almost, I don't know if that curve is becoming exponential, but it's definitely growing faster than linear. So I just want to talk about this program. Maybe you already know about this. NPTEL is offering what's called a certificate program. NPTEL Code is offering a certificate program on quantum computing. This starts in July this year, okay? And this is a set of 2 courses. Oops, sorry. So we've already run these introduction to quantum computing courses, like those are short-term courses, 4-week courses and so on. So this content is already available on YouTube for those of you who want to go, learn more about quantum computing. You can just Google Introduction to Quantum Computing NPTEL course. You'll find a set of lectures that were offered. These courses have run already, but they were just 4-week courses. But now we are running 2 semester-long courses, okay, one after the other, sort of going through all the details of quantum computing from the basics down to algorithms and so on. So this is the set of 2 courses that we have. So if you're interested, please go to the NPTEL website. This is NPTEL Code, and you can search for quantum computing, and you will this program will show up. I think the last date for registering for this is like mid-June, so you still have time to go register for these courses, certificate courses, okay? So yeah, I am one of the instructors, and then other colleagues both from here and from IBM India, because a lot of our demonstrations will be with the IBM superconducting qubits, okay? So yeah, you can email support elearn@nptel, etc. And here are some references on quantum computing if you're interested. So with that, thank you. So what we had planned for was at least one short demo on the IBM platform to show you what is possible, that everything I spoke about is actually something that's real and happening out there. So maybe we can just do one demonstration. I think we have half an hour. Is Wali, am I here as well? Okay, I don't see her. Yeah. Okay. Okay, maybe questions before that? Yeah. I'll just take two and then I'll let my student go ahead. Yeah. So in India, I think this is still at a bit of a nascent stage. We do have, I think at the last count, I heard there were 30 to 50 startups, quantum startups across the country. So some of them basically have to do with software, in the sense, how do you program a quantum computer, right? What are the kind of stacks you can build? Some of them have to do with what is called noise mitigation, error correction. There are a few which focus on building actual qubits. Some of these are photonics based qubits. I think there's even a startup which is talking about building superconducting qubits in India and so on. I am not sure how mature it is, to be very honest with you, but it's certainly something that exists today. 5 years ago, it didn't exist. And it is expected that this will only grow in the coming years. So, one startup that I know of, at least, has been fairly successful is in the area of quantum cryptography. There's a startup called QNew based in Bangalore where they build these quantum crypto systems. That's an area which I had no time to talk about today. But that's an area where industry is in general more advanced because it's somewhat easier to do these experiments. But so computing itself, I would say we are still at a much more nascent stage. Oh, there are some which do quantum machine learning and things like that also. Yeah. The earlier course was not recorded in 2017 or 19. It was actually recorded during the pandemic. So that was recorded during 2021. That's the NPTEL course that I'm talking about, which was a 4-week course that was jointly offered by IIT Madras and IBM. So the first edition of the course was recorded in 2021. It had a rerun last year, 2022. The course I'm talking about is a fresh course that we are offering now. Okay. Yeah. Huh. Okay, sorry. Yeah, whether Google really showed quantum supremacy. Okay, like I said, let's use the word quantum advantage because today supremacy has all kinds of strange connotations. Yeah, so quantum advantage. So Google, interestingly, did not demonstrate any of these algorithms, right? It didn't say that, okay, here is a factoring algorithm where I've beaten the best classical computer. Here's a search algorithm that I've beaten. It picked a task which was already, in a sense, tailor made for quantum devices. It picked a task which makes use of the intrinsic randomness of the quantum device. So, obviously, a classical device will take some time to generate that kind of randomness. And if you are talking a few handful of qubits, your classical simulators can still simulate it. But they were at a stage where they were at 72 qubits, of which at least 50 qubits were being used for demonstrating this task, which had to basically do with what's called random quantum circuits, predicting the outcome of a random quantum circuit. Classically, you will have to simulate a lot to get the outcome, but quantumly, it was just one run, obviously, and they could. Now, what IBM showed is that the complexity, classical complexity of that was not that high because they were only using 50 qubits. Okay, so the IBM counter, in my opinion, was not very sound because when you talk about computational complexity, see, it's like, what is the biggest number that a quantum computer can factor today? Debjyoti, 35. Now, obviously, you and I can do it faster, and of course, my classical device can do it faster. But that's because today we are at a stage where we are only able to use, say, 25 out of 100 qubits usefully. Let's say these 400 qubits, maybe we can do much more. Yeah. So the more number of, so this complexity is not decided by how many qubits you have today. Complexity is decided by how does the problem scale. So the problem that Google demonstrated scales exponentially. Okay, so the classical complexity will scale exponentially. So if Google had done the same task for 100 qubits, then it would have taken close to the age of the universe, even on the best classical devices, to simulate that. Having said that, last year, there was a new algorithm that was demonstrated, not by IBM, but by a Chinese group, which showed that the same random sampling task that Google had done, there was a much more efficient classical algorithm to do it. So now there's really a toss-up about whether that task really shows quantum advantage or not. The IBM counter was just to say, Well, your 50 qubits, I don't need age of the universe, I can do it in 5 days or something like that, right? But that's not how complexity is decided. Complexity is based on how it scales with the number, right? Okay. Yeah. 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 Correct. So it can break, yeah. Yeah. Okay, so two things. First, yeah, we do have something called post-quantum cryptography, where you design cryptographic protocols are which you try to make them provably quantum secure. Now, that is a very hard task. See, when I say factoring, for example, why did people pick factoring as a problem to do cryptography? Because it is believed to be hard on a classical device. Nobody knows of an algorithm which is more efficient than, say, the current one, which takes an exponential amount of time. Once Peter Shor came and showed that you can do factoring exponentially faster, that is broken. So today, the challenge of in cryptography, classical cryptography, is to come up with other schemes which can be provably quantum secure, and that is very hard. It is basically saying that there exists no quantum algorithm which can do this task exponentially faster. So it's a very strong statement that one has to prove. So while there are several candidates which people believe are hard for quantum computers, is there an proof that this is actually hard for quantum computers? No. So that's where research is at, right? So we still don't know that something is provably quantum secure. That is very hard to establish. Now the second aspect, suppose one comes up with a provably secure classical crypto protocol, then should we still be interested in quantum computers? Yes, because factoring is just one of the tasks that a quantum computer can do faster. Why were people interested in quantum computers? Even before Peter Shor, Deutsch's algorithm is 1980s. Why was Deutsch thinking about computing with quantum bits? The idea actually goes back to Richard Feynman. Feynman was interested in simulating a very hard physics problem called lattice gauge theories, right? They were trying to basically simulate particle physics on classical computers. And then they realized that this task is exponentially hard. It's extremely hard for classical devices. But then we believe that nature is somehow doing these computations, field theoretic computations, and arriving at the ground state, right? Because that's what we see around us. So Feynman's idea was that nature is somehow a quantum computer. So if one is able to truly tap into the quantum nature of particles and compute using their quantum properties, then we should be able to simulate physical systems much more naturally than what one is trying to do with classical devices. So this was the sort of underlying motive, and that motivation doesn't go away.
Just quickly go through how to do simple programs on a real quantum hardware. So what we'll be using is an IBM's quantum hardware. We'll be accessing it through the cloud. Since most of you have not yet been through the basics of logging in and stuff, so I'll start there. So what you initially have to do is just log into quantumcomputing.ibm.com. So you just have to create an ID for yourself, and you'll be given access to 7 or so systems. And this is just the usual procedure of logging in and stuff. Give your email ID, and then so once you log in, so you see a dashboard. What I want to show here is that, so what are you actually accessing are qubit systems, superconducting systems to be specific. And when you see, when you log in, you're basically given access to 7 qubits and 5 qubit systems, which means you can access whatever you learned so far as zeros and ones or single qubit. You have access to 5 or 7 qubits which you can use. Initially starting off, you can just explore what are the systems and connectivities that you have at hand. So let me just go to one particular system called IBM Perth. So this is a 7 qubit system. There's something called the quantum volume, which basically means how many qubits plus how many gates can you act on it. So that's the quantum volume itself. CLOPS is just a layer of operations per second that you can do and stuffs like that. So one thing that ma'am was telling was like realizing a qubit is really hard because you have all kind of errors there. So for example, this 7 qubit system has an hardware implementation which looks like this. These are the connectivities. So why are connectivities important is you have 2 qubit gates such as the C0 that ma'am was telling. You control with 1 bit and the target gets operated based on the control qubit. So that connectivity errors are also there. So which means that whatever circuit you create is undergoing a lot of errors, and that's what you see here as a color map. So you can just log in and look at what are the available resources that you are allowed to access. So these are 7 qubits and 5 qubits. So these are very basic stuffs. And then when you want to start off, it's better to look at an interface like this. So this is called the quantum composer. So how you get into it is once you log in, you see your dashboard, and then you just click on the composer. So the composer lets you put very basic elements on your qubit circuit and see what happens. So what I have here as Q0 is the qubit itself, which means these are quantum bits which can be in any states which are superpositions of zeros and ones and not just zeros and ones. Then there are classical registers. At the moment there are 4. That's not necessary. The classical registers are basically where you measure the qubit and you store the value in the classical registers. That's it. It's very simple as that. So what you have here, 2 graphs are, one is the state vector graph which tells you what is the state of the qubit. The other thing that you can do is probabilities. For example, if you measure your qubit, what is the probability of getting a 0 and 1? So why are these important? For example, an Hadamard is a gate that throws a qubit in a superposition of zeros and ones. So let's see what happens when you throw an Hadamard here. So initially when you start off, when you don't have anything on your circuit, your qubit is always in the 0 state. It's initialized in the ground state. Suppose you put an Hadamard, it's going to throw it in a superposition of zeros and ones. So that's what you see here in the probabilities. You see that there is a 50% chance of getting a 0 when you measure it, and a 50% of chance that you get a 1 when you measure it. So this is something that's not possible classically. The other thing that you can visualize is a state vector itself. So we saw how every state can be written as a column matrix, right? And that has values and even phase. So here there is no phase. Suppose it was a, so let's say my initial state was a 1. So this is the vector 0, 1, and now I do an Hadamard on it. It actually puts a phase of pi between 0 and 1. That's why you see in the state vector here. Suppose you are just looking at the probabilities, those are measurement outcomes. If you measure a minus state on a 0, 1 basis, you see 50% 0 and 50% 1. So this is one kind of representation. The other kind of representation is a Bloch sphere representation that ma'am was like telling about. So these are representation of a qubit on a sphere. So if you remember, the 0 was one of the poles and the 1 was the other pole. Let me just delete the Hadamard. And so now Q0 is in the 0 state, which is the north pole of the Bloch sphere. Suppose it was in the 1 state, then it's the south pole. So any operation is basically taking your state vector unitary, it's rotating on the Bloch sphere. So that's the idea of it. Suppose you put a phase of pi by 2, it actually doesn't do anything. So that's why your state is still in the 0. But suppose you put it on the 1 state, it basically flips your state and yet doesn't give any rotation there. So this was for someone who is starting off. For example, you want to see what quantum gates do to quantum bits, and this is where you start. So these are just basic operations. And then once you're done with single qubit and all the gates, all possible gates, what it does, you can go to 2 qubits. So C naught was the gate that ma'am mentioned, which means that based on what the control qubit state is, it does some operation to the target. At this point, the control is Q0 and the target is Q1. You can just play around and look that when you have one state on the first qubit, it does a NOT operation on the second qubit, and that's why you see the probability of getting 1 1 is 100%. So once you are familiar with the gates and stuffs, you can go on to just program it. So IBM itself provides a Jupyter notebook within its interface, so that's something where you can start. The first thing that you can do is you can play with the circuits here. You see the codes are written on the right side simultaneously. You can open them in the quantum lab. That is nothing but an Jupyter kind of notebook kind of interface where it will download your codes and then it will tell you how to code itself. In case you want to do it locally on your machine, then that's also fine. What you do is you go to your dashboard. So when you go to your account, you get an API token. You can you do the usual pip install Qiskit. The whole Qiskit is the package that gives you access to the quantum hardware, and then you can put your own API token there and create an account. Maybe I'll quickly show that, and then yeah, after your installation, basic installation is done, you get your Qiskit module through pip install or something. You can check your version and stuffs, and then what you do is you have to import your provider itself. And how you do that is, these are all basic stuffs. You can also see it, Google it up, and IBM has a whole YouTube series on this, so it's all there. Since many of you are new to it, I am just telling this. When you go to your account settings, you will have the access that you are allowed to use. So instances is where you can just go. You can copy your provider, and then you can put it here. It's just a copy paste, and then you get access to some number of hardware, and that you can print. You just have to give providers or backend, and then print all your backends that are available to you. So I'll just start with creating a basic circuit, and then you can go off from there. Any quantum circuit needs two stuffs. One is a quantum register, and then a classical register to measure the quantum register and store onto. So these are basic calls. You create a variable called like tell that's a quantum register, and when you put a 2 here, it means I have 2 quantum registers which are 2 qubits. And then classical register, I need 2 registers to measure it onto, so I use a 2 there. And then you create a quantum circuit. So what circuit I have created here is a very basic circuit called a Bell state. So a Bell state is nothing but you have 2 qubits, and it's in a 50-50 superposition of 0, 0 and 1, 1. So you have 2 qubits. These are something called entangled qubits. So anytime you measure one qubit in 0 state, the other qubit is also in a 0 state. So how you do it is using a non-local gate, which is the C0 gate. So here what we do is we call a quantum circuit consisting of 2 qubits and 2 classical registers, and then we put an Hadamard. Hadamard will throw the state into superposition of zeros and ones, and then you do a C0, which will do a NOT operation on the target bit based on the control bit, and then I'm just measuring it. So when you measure, you give the classical register, and you can draw the circuit very well. Now what IBM does it gives you access to simulators as well, which means you don't have to run it on hardware, because hardwares take a long time to run, because you have a lot of jobs that are already submitted and it stays in queue for a long time. So you have some 5 to 6 simulators available to you. So you can run all your circuits on a simulator and see how it works. So shorts is something that ma'am was telling, that quantum computer, when you measure it at one time, you only get one result. You don't know what are the possible results. So what you do is you run it 1,000 times, 20,000 times is max, is what I think. And then you plot a histogram and you get an idea of what is the circuit doing. So for example, I said this is a Bell state which is 0, 0 and 1, 1, which means every time I measure, the states are both in 0 or both in 1. So they're kind of entangled. So this is one. Entanglement is one of the things that you see only in quantum and not in classical. So if you all have the patience, we can go through Deutsch-Jozsa algorithm or. So the DJ algorithm was basically like you are given a function and you're asked to find whether it is constant or balanced. That whether you put all of the input and you get the constant output, or sometimes you get zeros and sometimes you get 1. So that was the idea of the DJ algorithm itself. The circuit which I think we didn't see was, this is how you implement the circuit itself. So the idea is, instead of giving the oracle just one input, we are going to give the all possible inputs, and we are somehow going to phase kickback. Okay, if the idea is not very clear, it means that we are going to use the phase information such that the phase will kick back onto the circuit if the function is constant or balanced, and it will give us some kind of result, unique result if it's constant or balanced. So that's the idea. This is something which is very basic, and you can find it in the IBM textbook itself. So IBM itself has a textbook called Qiskit textbook. So if you're interested, you can start off there. So what happens in Deutsch-Jozsa algorithm is, you start and the circuit basically looks like this. Suppose you have a 4-qubit input, you want to find whether 4-bit Boolean function, you want to find whether it's constant or balanced. What you do is, you first put an Hadamard on all the 4 bits. So what does this do is, instead of having it as 0, 0, 0, it has as all possible inputs. So 0, 0, 0 to 1, 1, 1, 1. So it's kind of like looking that you're giving all possible inputs to the oracle itself. So what I call as oracle here is, it will compute the function and then it will XOR with the y value, which is another ancillary input. So this is the difference between the classical and the quantum. You need an ancillary bit here, qubit here rather. So what happens is, you have a superposition of all possible inputs going into your oracle and one minus state going into your oracle. So a minus state is 0, minus 1. So it's a phase of pi between 0 state and 1 state, and it's a superposition state. So it so happens that when this oracle takes place and you do the measurement after creating, after doing another set of Hadamards, you see that there is only, when the function is balanced, you get all zeros, and when the function is not balanced, you never get all zeros. So that was the overall idea of the algorithm, but you really have to write down the math to see why it and how it works. So if you want to run a basic version of this on your Qiskit, I'll just show you a simple example. So after you've downloaded your package and all, you just import Qiskit and whatever is necessary, like NumPy and stuffs. Here I have defined balanced oracle and constant oracle, which means nothing that functions that give a balanced output and a constant output. You can create your own function. I think for this example, we can look at a concrete example. Let's say our function is x0 XORed with x1 into x2. So this is a balanced function actually, you can check. You can put all possible values of x0, x1 and x2, which are zeros and ones, and you see that half of the time you will get 0 and half of the time you will get 1. So how do you create an oracle is the question here. So what you see here is x1 into x2. So x1 into x2 is something like a Toffoli gate. A Toffoli gate is nothing but a double controlled NOT gate. So you got a C NOT, which is single controlled. A double control is you control the NOT operation on the third qubit based on whether the first and the second qubit are in the 1 state. So this is something you can again work out, see that the Toffoli gate does this operation, and then a C NOT between the 0 and the 3 will do XOR operation between these two. So this is something you need to check, but these are basic stuffs. So this is our oracle here. So what I had as a box there is just this. It just implements the function and puts the value on the 4th qubit. So this is a 3-bit Boolean function, and the 4th bit is to put the answer into. So this was the quantum oracle part, the one between the barriers. The first 3 Hadamards, what does it do? It puts the initial 0, 0 state into a superposition of all possible state. So what goes into oracle is a superposition of all possible inputs. The final state is in a very it's a very intelligent choice of the ancillary bit to be in the minus state, because when you write it down, when you write the vectors down, the face down, you notice that this minus face is what causes the face to kick back, and when your function is balanced, it cancels out every other probability and you get only all zeros. So that's an intelligent choice of the ancilla. And then you do again, you reverse the Hadamard's and then you measure. So when you measure, you ideally have to get, it's a balanced function, so you get all zeros. So that was the idea. So what I've defined here as a new oracle is the same oracle that is done for the 3-qubit Boolean function that we saw, x1 XOR with x2 into x3. And then you can define functions for producing the initial superposition. It's nothing but you first call an quantum circuit and then you do X operation on the last bit because you want a minus state there, and then you put an Hadamard on all the possible first qubits, so initial superposition H. You create a barrier to know where your initial superposition is, where your oracle is, and where your final measurement is. That's it. And then you put it all together. You can also draw your circuit here. How you run it is you call a backend. So backend is nothing, at this moment I'm using a simulator because that's easier to get the output. Then you get the result. It's all simple. The syntax is like you get used to it once you start doing it. You execute it and you get the counts, and you see that there is a probability of non-zero probability of getting all zeros. So it's a balanced function. So that this shows you how powerful it is. Just with one quantum use of the oracle, we're able to find whether the function is constant or balanced.